So up until now, we've been concentrating on mostly numerical variables. We looked at confidence intervals. We looked at comparing means of two groups using hypothesis testing, using the t-test. We looked at comparing the means of more than two groups using analysis of variance. You really are comparing the means of group A, group B, group C, group D, and so on and so forth. But again, they're the means, and the means we're talking about strictly numerical variables. So it could be blood pressure, could be the level of an enzyme, could be the amount of lead in someone's blood, and so on and so forth. But it's a numerical measurement. SPSS calls that kind of variable a scalar variable. It's kind of a combination of a numerical variable and a categorical variable, because inevitably, when we're comparing, that implies we have groups. We're comparing one group to another group, or one population to another population. So when we have an SPSS file and we're doing a t-test, we might be comparing two groups such as by gender, male and female, for instance. And we might be looking at the height, the weight, blood pressure, and so on and so forth, which are numerical variables, which you describe as a center of by an average, and the variability by using the term standard deviation, or sigma if we're talking about the population standard deviation. So so up until now, the tools that we've been using are tools that are intended to be used to examine groups, either two with the t-test or more than two with analysis of variance, with regard to the middle of those groups, the mean of those groups. Is the mean of group A the same or different than the mean of group B? Well, we've ignored up to now the situation where we might not be dealing with a numerical variable, where we might be dealing with a categorical variable instead. So for instance, diabetes. If you diagnose someone with nowadays, I don't know if you guys are younger, so when you go to the doctor, you don't get bad news from your doctors. You only get good news when you're young from your doctors. But as you get older, you learn, they give you all sorts of new stuff. Like half the people I know, they go to their doctor, they come home discouraged because they were told they're pre-diabetes. I don't know what pre-diabetes is, because if you don't have diabetes, but you're pre-diabetes, what does that mean? I mean, does it mean that you have diabetes or you don't have diabetes? And then, is there a pre-diabetes? So if there's a pre-diabetes, there must be a pre-diabetes, right? So I mean, it seems a little silly, right? So at any rate, I think it's just basically a technique that they use to scare everybody into eating less sugar and exercising more. But at any rate, in the old days, when things were a little bit more reasonable, you either had diabetes or you didn't have diabetes. You pretty much, and we know that that's really kind of a moving scale, right? So we know that blood pressure years ago, like high blood pressure might have been one level, and now they're more conservative. They consider treatable or high blood pressure a lower level than they did. Just like cholesterol, over the years, the levels of total cholesterol that they felt were safe have lowered over time, but they've set a limit. So generally you go to your doctor and he either tells you you should get treatment or you shouldn't get treatment. So let's go back to the old days where it's relatively simple. You either had diabetes or you didn't have diabetes. Okay, so let's say we wanted to compare two groups with regard to whether or not to have diabetes. Well, diabetes is that diagnosis, that you could call it a diagnosis which is numerical, like fasting blood sugar or something like that. But for the most part, we usually describe the prevalence of diabetes as people who either have it or don't have it, as a proportion. So we can have two groups, say males and females, and we can randomly select those two groups, those two populations, and say to ourselves, I want to determine whether the rate of diabetes is higher in women than in men. What do you guys think? Do you think it's higher in women or men? What would you guess? Women, because you got pregnancy-related diabetes, right? Not also that the population of women live longer. So, diabetes is very frequently associated with older ages. So maybe there is a difference, right? So this is not a ridiculous study, right? So it's something that you might actually want to know. So how would we determine that? Well, we want to compare the rates of diabetes in women in a population and males in a population. So let's say that we go out and we sample 100 women, randomly sample 100 women from a defined population. That might be women in Brooklyn between the ages of 40 and 80, and men in Brooklyn between the ages of 40 and 80. Right? Might even narrow it down a little bit, but we collect census data, we locate them, we get their phone numbers, we randomly canvass 100 people, 100 women and 100 men in that population. So now each one of them, we call them up and they respond to our questionnaires. Have you ever been diagnosed with diabetes? Believe it or not, New York City Department of Health actually does this. They actually randomly call 8,000 people, more than 8,000 people every year, and they do a survey, a health survey. And we're going to be working with that community health survey that New York City does. It's going to be a data source for us. We're going to use it to maybe play around with some of the data, maybe do a little bit of a project or something like that. But next week, we'll really get into that and see how that's structured, how we can get that data, how we can import that data into SPSS and so on. So we're doing our own study. It's only 100 people each. So each is going to respond to the question, have you been ever diagnosed with diabetes, with either a yes or a no? That's the only choice we're going to give them. Right? Some of them maybe don't want to answer at all, so they won't wind up in our data. But the suitable answers are yes and no. So we will have 200 people, 100 males, 100 females, who have told us, yes, I have diabetes. No, I don't have diabetes. So now we need to compare those two groups to see if there's a difference in the rate of diabetes between male and female. So what's our exposure there? The exposure is gender, right? Gender, we're looking to see if gender is a risk for being diabetic, and what the relative risk between these two populations is. So on the other hand, each one of them is going to answer yes or no to whether they have diabetes. So we have a second variable, diabetes, yes or no, and gender, male or female. Both of those they're not numerical variables anymore, are they? Even though when we put it into SPSS, we may define it using numbers. In other words, 1 represents male, 2 represents female, 1 represents diabetic, 2 represents not diabetic. We may represent it with numbers, but really it's words. It's a nominal variable, a categorical variable. Diabetes, yes or no. Gender, yes or no. So now we no longer have a number that we can find an average of. In other words, an average of male or female doesn't mean anything. Average of diabetic or not doesn't mean anything. We might compare proportions. What percentage of males have diabetes? What percentage of females have diabetes? How do those two percentages compare to one another? But in this case, the tools we've learned so far, the hypothesis testing using the t-test, whether it's a single sample, independent samples, or paired samples, and the analysis of variance, which again is just another way of saying compare means, right? The word analysis variance kind of obscures the fact that it's really comparing means of different groups, except in that case, you're looking at many groups rather than just 2 groups. So we wind up with a situation where now we have a whole new class of variable that we need to work with, right? And we have tools for doing that. We're going to start to learn those tools. A lot of data that you might collect in a survey, for instance, is going to be categorical and nominal variables. Maybe some of it ordinal variables. That's a little bit different than just categorical, right? It's got special properties, and then has a relative order that a natural order that it takes. But for the most part, very often you will find information that is literally categorical variables, and you're going to want to compare different groups to see whether or not they vary with respect to one or more of these variables. So I am going to invent as just out of the blue, exactly this situation. I'm going to take exactly this situation. Actually, we have some other files here and stuff like that, but since we're talking about this, I'm going to take exactly this situation, and we're gonna sit here and we're going to invent a way to analyze this kind of data. Okay, so let me change colors here. This pen, I'll use blue. Okay, so let's say that we sample 100 males, and we sample 100 females, randomly sample from these populations. Okay, and I find that of the males, 40 say they have diabetes. Oh, shoot, that's kind of a high number. Let's say 30. Let's say this is an elderly population. I want to work with a little bit bigger numbers. Let's say this is males 60 to 80, and this is females 60 to 80. Okay, so let's say 30 males say they have diabetes, and 70 males say they don't have diabetes. Diabetes plus, diabetes negative. Okay, and how about females? Females, let's say among the females, we find that 40 say they have diabetes and 60 say they don't have diabetes. Well, now if I took another 100 females, and let's say I took another 100 females, right now it looks like the prevalence in this elderly population of females, it looks like the prevalence of diabetes in this population is 40%. Whoops, oh my goodness, what did I do there? Can I undo that? I don't think I can. No, I can't. Okay, we're going to have to look past that. Let's say in this population, the prevalence is 40%, 0.40, and the prevalence of males 0.30. If I would take a new sample of 100 women, and I know the prevalence is 40%, I would say to myself, or actually I know the prevalence of my sample, previous sample, was 40%. The second sample, would I expect to get exactly 40 females out of 100 that are diabetic? No, right? Would make sense, right? Because there's a certain amount of variability in sampling. I might get 39, I might get 42, I might get 50, I may get 38. I don't know because I really haven't taken a second sample, so I don't know how variable, these samples really are if I kept taking them over and over again. All I know is what I got on my first sample. So I'm going to look at this a different way. I'm going to say to myself, okay, I'm going to add all these together, and I'm going to say there are 7 out of 200 people, out of a total of 200 people, 70 of them said that they were diabetic, and 130 said that they were not diabetic. So the overall prevalence is 35%. Okay. Remember when we were working with diagnostic tests, we set up something that was a crosstabs or a table, right? And that table was 2x2 table. I'm going to do the same thing. In fact, the top part of this table, the columns are literally the same thing. Disease or not disease, right? Diabetic or not diabetic. The rows are the exposure. And what are the exposures? The exposures are gender, female or male. Okay, so how many total people do I have here? How many total people have I surveyed? I surveyed 200 people all told, right? What was the prevalence overall? 35%. So out of 200 people, I would expect 70 of them to be diabetic and 130 of them to not be diabetic. Okay. Well, now complicating factor here, 100 of them were female and 100 of them were male. If there is no association between gender and diabetes, I'd expect them to both get diabetes at the same rate. What rate would that be? That would be 35%. That's what my expectation would be if there's no association, right? So out of 100 females, I would expect 35 to have diabetes, and I would expect 65 to not have diabetes. Same with the males, 35 and 65. These are my expected values. Okay, so now I'm going to set up another table here. And this table is going to be my actual values. It's still going to be 70 and 130 and 200, right? Except this time, and it's going to be 100 females and 100 males, right? Female and male. Except this time I'm going to put in here the real numbers that I actually got when I collected this, right? So what was that? The real numbers were for males was 30 and 70, and for females was 40 and 60. Okay, so these are my observed values. Okay, great. So now look at the difference in these two tables. If these are my expected values, what I would have expected to get, but then I take an actual sample and I get these values, again, I wouldn't, even if this were true, even if there was no association, it didn't matter whether you were male or female, they both get it at the rate of 35%, right? They both diagnosed at the rate of 35%. Even if this were true, when I took a sample of 100 people, 200 people, 100 males, 100 females, I wouldn't expect to get exactly my expected values. I'd expect to get close. I might get really lucky and get exactly the expected values when there's no association between males and females, but no association between gender and the disease. But I'd expect a little bit of a difference, probably, right? I might get exactly the same thing, but more likely it would be different, but close to what I would have expected. Now the question becomes, how different is too different? How different do my observed values have to be from my expected values for me to say that there's a difference in the rate at which females get diabetes and males get diabetes? That makes sense to you? That now what we're really interested in is how different is this from what we had expected to see if males and females were getting diabetes at the same rate. So we got to figure out, how are we going to determine how different are these? Okay, so I'm going to redraw this on a new piece of paper. Okay, so here's my table. Here are my two tables again. Okay, this is disease plus, disease minus. This is female, this is male. Disease plus, disease minus. This is female, this is male. This is my expected values. This is my observed values. Okay, so this was the expected values were 35. I would expect to get at the same rate, 35, 35, 65, 65 out of 100 males and females. This is 100. This is 100. And I actually found 40 and 60 for the females and 30 and 70 for the males. Okay, so now how different is too different? Okay, so now we're going to invent a new statistic. Okay, we've called stuff T and F and so on and so forth. This one we're going to call chi-square. Right? Seems a little bit of a stretch, right? To call it chi-square. Where did that come from? But we're going to call it chi-square, right? Kind of an X with that's a Greek letter X with a capital X with a and squared. Okay, so I'm going to say to myself, the bigger the differences are between this table and this table, the more likely it is that males and females really get diabetes at a different rate. The smaller the differences between these two tables, the less likely it is that they get diabetes at a different rate. So I want chi-square, in order for me to say that the rates of getting the disease are different for the males and females, I want chi-square to be a big number. If it's a small number, I'm not going to feel comfortable saying that they're different. Well, what does that lead you into thinking about here? That leads you in thinking, maybe I should formalize this. Maybe I should have write out a null and an alternative hypothesis and determine what level of confidence that I want to be at that I can reject the null hypothesis, like alpha is equal to 0.05, just like our t-test or analysis of variance. So what would our null hypothesis be? Well, it's kind of hard to articulate it in terms of numbers here, like mu1 equals mu2, because we're not dealing with means, right? So why don't we say instead that the null hypothesis is there's no association between gender and diabetes. And my alternative hypothesis is there is an association between gender and diabetes. Okay, so and we want to be 95% certain before we reject the null hypothesis. In other words, we want to make sure there's less than a 5% chance that we would make a mistake and reject the null hypothesis here when we really shouldn't. Okay, so how are we going to do this? Okay, so let's see how I'm going to do this. I want the thing that's of interest to me here is I got to stay away from this thing because it writes if I'm too close to the surface. The thing here is I want to see how different each one of these boxes is from the box down here, and I'm going to put the difference together. Okay, so let me see the difference here. The difference between this box in our expected values and this box in our observed values is I'm going to start with the observed values and subtract the expected values. So 40 minus 35 is minus 5, right? I want the numbers to be bigger, right? The bigger the difference is, the more certain I am that there's a difference between what you would expect if there's no association between gender and disease and what you would expect if there is a gender. Well, how about this next box? 30, and I'm going to take 30 and subtract 35, that's negative 5. And then I'm going to go to this box, 60 minus 65, wait a second, 40 minus 30, that was a plus 5, the first one. 40 minus 35, that's negative 30 minus 30 minus 35 is negative 5. 60 minus 65 is negative 5. And 70 minus 65 is plus 5. Okay, so let's add up all the differences. I add up all the differences, I got a problem, it comes out 0. Right? Same thing happened when we had sum of squares. Remember we tried to do sum of squares? When we did the sums of the differences between the means in each of the individual values, what did I do to get rid of the negative signs there? Well, one thing you could do is do an absolute value, but in statistics, often what we do instead is we square the values. Okay, so I am going to say, instead of this, I'm going to say, let's take 40 right here, 40 minus 35, 5. I'm going to take that 5 and square it. And then I'm going to take the 30, and minus 35 is minus 5 squared, which is going to be plus 25 anyway, right? And then I'm going to take 60 minus 65, that's minus 5 squared. And then I'm going to add to that 70 minus 65 is 5 squared. So all of these get squared. So it's 25, 25, 25, 25. We add them all up together and it's 100. That's great. So now I eliminate the fact, and the bigger this number becomes, the bigger this is. Right now it's 100. If we're 200, it would mean the differences between these two tables even bigger. So I can have more confidence that there is a difference between males and females in the rate they get diabetes. Right, so I want that number to be a big number. Okay, now the only problem is that just as before, I've squared this number, and now it's out of all relationship to real difference, right? So what I did last time, sum of squares, we divided by the sample size. In this case, what I'm going to do to bring it back down into the range of the numbers we're dealing with here is I'm going to divide it. Each cell I'm going to divide it by the expected value. Okay, so in other words, this would be 25 divided by 35. This would be 20 divided by 35. 25 divided by 35. This would be 25 divided by, that's the negative one, 25 divided by 65. And this would be 25 divided by 65. Right? So I'm going to take each one of them, divide it by the expected value. So that's going to bring it back down into close to the area where I would be working, right? What did I just do there? I just created, okay, then I'm going to add them all together. Instead of adding them all together again 100, I'm going to add these together. Okay, it'll still be a window of how big the differences are, but now the numbers will be in the range of what the real differences are. So 25 over 35, what does that come out to anyway? Let me get my calculator out. I gotta turn off my pen first. Oops. 25 divided by 35 is equal to 0.71. I'm going to just remember that. And 25 divided by 65. Oops, not close enough. Well, I blew that. 25 divided by 65 is 0.38. I use 0.38. My trackpad's a little sensitive. Okay, 0.38. So this was 0.71 plus 0.71 plus 0.38 plus 0.38. Let's see what that adds up to. I'm going to do this without messing it up. Clear. 0.71 plus 71 plus 0.38. 0.71 plus 0.71 plus 0.38 plus 0.38. That adds up to 2.18. I did a lot of rounding there, but it runs up to about 2. What did I say, 2.18 or 2.38? 2.18. Okay, so that's the number I wind up with. What did I just do? If I did this, if I wrote this down as a formula, what did I just do? I took the observed value minus the expected value, squared it, and divided by the expected value, right? But I did that for each of the 4 boxes. So one of the ways I could indicate that is by saying that this chi-square is equal to the summation of observed values minus expected values squared over the expected values for each of the 4 boxes there, for n equals 1 to n equals 4, each representing all the boxes, right? So I would do that 4 times and just add them all together. That's what that formula represents. That's the formula of chi-square. I mean, we could have invented that. We didn't need some scientists from the 18th century to figure this out, right? We could have done this ourselves. Now, the complicated part, which is nice that they figured out that we don't have to, is how big is big enough for this number? Is 2.81 big enough for me to say that there's a difference between the rate at which females get diabetes and males get diabetes in these 2 populations? That's the tough part, is whether or not this is. So how did we deal with this before? Well, we dealt with it by having a table that we could reference that gave us the probabilities. In other words, there was a distribution associated with each one, with the outcomes for the t-test, for chi-square. So for the t-test, we had the z-score when we have very large sample, and the t-tables. And for analysis of variance, we had the F tables, the analysis of variance tables, where we could use this number of groups and the size of the samples and determine what the critical value that we needed for the analysis of variance was, that F statistic, right? Well, now we need to know what's the critical value for chi-square. What is that going to be equal to? Well, there are tables for that. I'm going to pull up the table now, but right after I pull up the table, I'm going to tell you how the table ties into all of this. Okay, so first let me pull up the table so we can get a look at this. Okay, chi-square table. Okay, here we go. Here's the table for chi-square. Okay, here we are. I don't want to erase that yet, so we're going to have to kind of look around it. So at the top here, actually what I can do, accurate, do I need that? Okay, we'll just have to rough it. So at the top here, I'll bring it up here. At the top here, you can see probability of exceeding the critical value, okay, and degrees of freedom. So we have to determine what the degrees of freedom are going to be. The degrees of freedom for the chi-square test is the number of rows minus 1 times the number of columns minus 1. So how many rows we got? 2. How many? That's minus 1 is 1. How many columns do we have? 2. Minus 1 is 1. 1 times 1 is 1. So we have 1 degree of freedom. That's the definition of our degrees of freedom for chi-square. So we're only dealing with 1 degree of freedom. What level of certainty for rejecting the null hypothesis did we set for ourselves? Well, we set a confidence level of 95% or an alpha, a maximum alpha error of 5%. So that's going to be 95%. So where is 95%? Probably. So here we got 5% right here. That's our alpha error. This would be if we're 90% confident, alpha is 10%, or 97.5%, or 99%. We have a column for each one of them. So for 1 degree of freedom, what is the critical value of chi-square that we have to exceed in order to be able to say that we would only get this big a number for the overall difference between these two tables if the null we would only that this would only occur less than 5% of the time if the null hypothesis were true. Well, in this case, it's 3.84 is my critical value for chi-square. So let me get this out of the way. Okay, so my critical value for chi-square is equal to 3. Whoops. Uh-oh, something bad happened here. Disconnect this and reconnect it. See if I can't get it to get happy again. It's only letting me draw straight lines for some reason now. Let me just see if I can't take care of this by turning that off. Nope, still not working. Okay, I'm gonna have to use my trackpad. Okay, so this is 3.84. Okay, so now, what did I actually calculate my chi-square value to be? 2.18. So I can't say with the level of certainty that I need, in other words, my chi-square number, the difference in these tables is not different enough for me to say that I would only get this outcome less than 5% of the time if the null hypothesis were true. So I can't reject my null hypothesis. There's better than a 5% chance that it is true. So I fail to reject my null hypothesis. So if these numbers had been more different, then the values, the differences in the values between each cell would be different. We'd square it, it'd be a different number. We divide by the expected values, so we could produce a different number. We add them together and we get a different number. If we had gotten a number like 4.1, could I reject my null hypothesis then? Yeah, because there's less than a 5% chance you would get that big a difference between these two tables if the null hypothesis was true. Okay, how about you guys online? Does that make sense to you guys? I'm going to clear this out. I'm hoping to get a response. Are you guys okay with that online? Hard to tell. Hard to tell whether it's a lag or if they're in the kitchen getting lunch. But at any rate, so I just wanted to draw a little bit of a sketch for you. Okay, now the chi-square table, chi-square, basically what you're looking at with chi-square is that the likely, oh, good, I got a reply. There you go. Okay, good, thank you. So the likelihood that you would get it's kind of similar to the analysis variance. The likelihood that you would get zero difference between the two tables, it's not zero, but it's not that likely, right? So if this were the probability going up in this direction, and this were the actual chi-square value, the number that you got for chi-square, well, then you'd expect it to start, not all the way down here, it's zero probability, but maybe up here. And then you'd expect it to go very sharply for a small difference. But then as the difference got bigger and bigger and bigger, you'd expect it to go lower and lower and lower. It's asymptotic. It doesn't really get to zero. But the value of chi-square that you need is going to be the value, in this case 3.84, is the value that you need to say that only 5% of the time, if the null hypothesis was true, would you get a chi-square result. That's that big when you compare the two tables. So if you're over here, it can only come up 3% of the time, you know that's only a 3% chance that the null hypothesis is true. So you can reject, since you're willing to take a risk of 5%, you can reject the null hypothesis. Now, you notice that we talked about degrees of freedom. The degrees of freedom is equal to rows minus 1 times the columns minus 1. Well, what does that imply? That implies we don't have to have just 2 by 2 columns. We can have any size table we want. We can compare males and females for, let's say, I'm trying to think of the categories that would have more for, let's say that we were looking at birth weights by ethnicity. The outcome is the birth weight, and the risk is the exposure is the ethnicity. So we could have, say, 5 different ethnic groups: white, black, Hispanic, Asian Pacific Islander, say 4, and then that would be 4 rows, and then we could have, say, 3 columns: premature, underweight, and normal, right? If we categorize them that way. So again, we're not looking at scales or real numbers. We're looking at categories in both directions. And in that case, it would be a 4 by 3 table, 3 columns and 4 rows. And the thing that would change there is not how we do the analysis. Right now, instead of having four cells to compare, now we're going to take the observed minus expected squared over the expected, but we're going to do it for 4 rows, 3 columns. That's going to be 12 different cells. Since you're doing it for 12 cells, then by nature, it's going to be a bigger number. So what's going to happen is the critical value for chi-square is going to be bigger based on the number of rows and columns that you have, right? They're still working with categorical variables in both cases. So what would that be? That would be 4 minus 1 is 3, and 3 minus 1 is 2. So 3 times 2 is 6 degrees of freedom. So if I get my table back, the critical value for that situation would be, and let me get my pointer, critical value for that situation would be, what I say, 3 times 2 is 6, would be, here's 6 degrees of freedom, would be 12.6. You'd have to exceed the chi-square value of 12.6 in that situation. A lot of the studies you're going to do are going to be 2 by 2 tables, but on occasion, you're going to wind up with a situation like that as well. Okay, so the numbers I made up in my head as we worked, turns out it didn't wind up making, wasn't enough of a difference to say that we could say for sure, or at least at the level that we're comfortable with, that there was a difference in the rate, the prevalence of diabetes in those 2 populations. So now I'm going to take a look at those numbers again. Let me clear this out. I'm going to take a look at those numbers a different way. I'm going to take my observed values again. Okay, I'm just going to take my observed values. I don't think my pen is not cooperating here. Yep, it's not cooperating still. Let me see what I might have to do here. Let's disconnect it and let's reconnect it, see if that does anything. Nope, still only let me draw straight lines. Oh, I have to go back here and turn this pen off. Oh, there we go. Nope, it's not there. If there's a way I can uninstall and get it to stop looking at this. Okay, I don't want to play with this too much right now. Okay, so let me erase this first. Okay. So again, I'm going to have to stumble along with the trackpad. But, okay, so let me recreate that table again using my fingertip instead. Okay, this is diabetes. Yes, you got diabetes. This is diabetes negative. I got a plus in there so we can see it. And this is female. And this is male. And again, this is I'm going back to my observed values. Okay, and for females, it was 30 and 40 and 60 and 60. And for males, it was 30 and 70. Okay, so if I were to ask you, if you're a female in this age group, 60 to 80, I think we said, what's your risk for having diabetes? What would your risk be equal to? And I'm gonna redraw this down here, except in this table, I am going to put, instead of numbers, I'm going to put letters. A, B, C, and D. Okay, and in each one of these, we got 100 people, right? And this is 100 males. Okay, and this over here, outside here, would be A plus B, right? So 100, so this would be A plus B there, and this would be A plus B here. Getting cramps in my finger here. It's not exactly ergonometric. So at any rate, so what would be your risk of having diabetes if you're a female in this population? Well, the risk would be, in this case down here, the risk would be A over A plus B, right? In other words, 40 people out of 100, 40 females out of 100 have diabetes, so it would be 0.40. That's your risk, 40%, right? And for males, same thing, A over A plus B would be 30%. Okay, wow, that's very interesting. There's a difference there, right? You know what I'm going to do? I'm going to say to myself, I'm going to create a new term that I'm going to call relative risk. And it's going to be really handy. Relative, oh boy, that's ugly. Take my word for it. That's what I'm writing there. Okay, so hopefully you can hear me while I'm writing this. Relative risk. Okay, and my relative risk is going to be A. Whoops, I'll do it down here. A over A plus B for females divided by A over. Excuse me. This is C plus D. You guys need to correct me when I make these silly mistakes. I'm old. I'm depending on you to do this. C over C plus D. Okay, basically what it winds up being is 40% divided by 30%, 0.40, right, over 0.30. Okay, now most of you guys are not going to have to look at this down here, but if you need it as a crutch, if you don't want to, if you're having trouble and you need to remember it, you can kind of use this table with the A's and B's as kind of a backup of how to determine these various things. Okay, so 40 over 0.40 over 0.30 is equal to 1.33333333, right? Continues along. What does that tell you? That tells you the risk of being diabetic is 33% higher for females than it is for males. Isn't that easy to wrap your head around? In other words, we see that all the time on the news. A new study just came out. If you're a smoker, your risk of lung cancer is 7 times, maybe not 7, 5 times what it is for someone who doesn't smoke. Your risk of mesothelioma, if you're an asbestos worker, is 7 times what it is for, 30 times what it is for people who don't work with asbestos or don't have a significant asbestos exposure. It's easy to wrap your head around those kind of statistics, right? This is called relative risk. Sometimes you'll hear it also called risk ratio, right? It's the ratio of the two risks, risk for females and risk for males. So either term's interchangeable, and it's really convenient because they're both RR, right? So easy to remember, relative risk or risk ratio. Okay, so now, well, that's very interesting. The only problem is that how do I know that that risk ratio is big enough for me to know that it's not, that risk is not due to chance? In other words, it would be nice if it were double, 2, because it would be a bigger difference. It'd be more comfortable. I need a null and alternative hypothesis for the risk ratio, right? So what would my null and alternative hypothesis be for the risk ratio? So what do you think, if there's no difference for the risk between males and females, what do you think the risk ratio would be equal to? What would it be equal to if this is 35 out of 100 and 35 out of 100? What would it be? That'd be 0.35, that'd be 0.35. If there's no difference, it's the risk ratio is 1. The ratio of the risk for females over the ratio of the risk for females divided by the risk for males is going to be 1. It's going to be the same. So anything divided by itself is 1, right? So the null hypothesis is that the risk ratio is equal to 1. And what's our alternative hypothesis? That the risk ratio is not equal to 1, right? So can I say that the risk ratio is not equal to 1 here? What am I missing here? What do I need to know in order for me to know that there's less than 5% chance that the risk ratio in this situation is less than is not 1? What do I need to know about that 1.33? Remember when we were looking at means and we wanted to see whether a mean was different from a different mean, or when we had a proportion and we wanted to have an idea of, you know, what the real proportion might be? What did we calculate in those situations where we took a sample, we got a mean, we took a sample, got a proportion? What next step did we take to show how well we knew what the actual population mean was? We calculated a confidence interval, right? So what we need to know is not just that this is 1.33. We need to know what the 95% confidence interval is for this, right? So based on what happened, so I'm going to say 95% confidence interval. So I'm going to give you 2 possible confidence intervals. I'm going to ask you to tell me, based on the numbers and what we've done so far, I'm going to say 0.8 to 1.9, and I'm going to say 1.1 to 1.8. Okay, so which of those 2 confidence intervals you think is more likely to be correct for this situation? What happened when well, first of all, which of these two would allow me to reject the null hypothesis? Right? My null hypothesis, the risk ratio is 1. Remember, alpha is equal to 0.05. Right? 0.05. So I need, for my confidence interval, to not my 95% confidence interval to not include the number 1. Right? If it includes the number 1, if the confidence interval includes the number 1, I can't say with 95% certainty that it's not 1, because 1 is inside my confidence interval. But if 1 is outside of my confidence interval, I'm 95% sure that the true risk ratio is different than 1. So this one allows me to reject my null hypothesis. So which of these two, based on what we did previously with chi-square, which of these two confidence intervals you think is more likely to be, if I calculated the real confidence interval? We can do it as these are proportions and stuff like that. We kind of learned how to do it. This version is a little bit more complicated. In real life, we're just going to, for our class, we're just going to use SPSS to calculate the confidence interval. So we're not going to do it. But which of these two you think is more likely to be the correct confidence interval for this situation based on what happened with chi-square? Was I able to reject the null hypothesis with chi-square with these numbers? No. So what about now? Should I be able to reject the null hypothesis now? It's the same numbers. I should get the same result. So I should not be able to reject the null hypothesis. So it's more likely it would be something like this than something like this, which would make the two tests conflict with each other. Okay, so that's not that hard, right? In other words, you know, when we get SPSS to calculate the confidence interval for us. So again, we failed to reject the null hypothesis in this case. Okay, so now we got another thing we're going to work on now. So now, you know, this was really pretty. This was really pretty easy to do, right? So of course, in statistics, since it's easy and makes sense, we have to make it harder. Okay, so we're going to look. So far, we've looked at chi-square. We've invented chi-square, and we've invented another statistic called relative risk, which is great because it's really easy to understand. You know, relative risk. You're twice. So in other words, if this had been 40 and 60, and this had been 20 and 80, that would be 40% and 20%. So you'd be 40% over 20%. You'd be twice as likely to have diabetes if you're a female in this population. Really easy to understand. So now we're going to invent another statistic. Okay, and in this statistic, we're going to look at, instead of risk, we're going to look at something called odds. Okay, so what's the difference between risk or an odds? Well, the way we're going to determine odds is, instead of A over A plus B, the odds of having diabetes are going to be A over B for the females and C over D for the males. And what's that going to be? Well, that's going to be 40 over 60 for the females, okay, which is equal to 0.66, 0.67 actually. And for the females, it's going to be 30 over, for the males, 30 over 70, which is, I got to calculate that one. I'm sorry, it's a point, yeah, it's 0.66. 30 over 70, which is equal to, okay, let's figure out what that is. Clear. 30 divided by 70 equals, oops, hey, 30 divided by 70 equals 0.43, I'm going to call it. Equals 0.43. And our odds ratio is going to be, what's our odds ratio going to be? Well, it's going to be A over B the odds for females divided by the odds for males, C over D, which is 0.67 divided by 0.43. And that's going to be equal to, okay, let me get my calculator back. Uh-oh, what did I do now? Oh my goodness. I don't want to continue. What have I done? What is that? Where'd that come from? Okay, let's see. .67 over 0.43. 0.67 divided by 0.43. You know, normally I would not round until I was at the very end, if I rounded at all. But I want to make this go as smoothly as possible. I'm just going to call it 1.6. I would normally, like on a test, you would say 1.56 or something like that. Okay, I'll say 1.56. What the hell? Try not to write too much here because it's painful. 1.56, right? So my odds ratio, the ratio of the odds if you're female versus the odds if you're male, the odds ratio is 1.56. What was the relative risk? The relative risk was 1.33. The odds ratio is 1. They're kind of similar, right? And I mean, we get the same kind of thing from them. We get a slightly different number, but they're similar ways of demonstrating the same thing. What do you think the null hypothesis would be for the odds ratio? What would we expect the odds ratio to be if the null hypothesis were true? Odds ratio is equal to 1, right? We'd expect the same odds for both of them if the null hypothesis were true. In other words, there's no difference for male or female. And if there is a difference, the odds ratio is not equal to 1. Would be our alternative hypothesis. And again, in order to decide whether to reject the null hypothesis, odds ratio is equal to 1, and accept the alternative hypothesis, odds ratio is not equal to 1, we would have to know the confidence interval for the true odds ratio, right? And again, chances are it's going to be one that does not include 1, because we already know the numbers that we're working with don't allow me to reject the null hypothesis the other ways, right? So you would have to calculate those odds ratios. To put odds, now it's seems a little weird. You know, most studies, rather than use relative risk, which was to me as a non-statistician, I don't work professionally all day long as a statistician, thank God, but to a peripheral statistician, right, rather than a central statistician, to me, relative risk is much more descriptive, much easier to understand, much easier to convey to a layman what that means. Odds ratio, however, is more popular for a bunch of reasons. One of these days, maybe we'll get to it. Maybe we'll discuss some of the reasons why odds ratio in studies is a bit more popular. So you'll see a lot of studies where they will say that we compared the rate of diabetes in Hispanics to diabetes in Asian Pacific Islanders, and we found an odds ratio. We found a difference in the rate, an odds ratio of 2.3, and in parentheses they'll put a confidence interval for that of 1.5 to 3.0, which would indicate to you that it's different than 1, that it's a statistically significant odds ratio. In other words, the chances that the null hypothesis were true, that there was really no difference, even though they got numbers that appeared to be a difference of less than 5%, right? So that's how we use odds ratio. Now, to put odds into perspective, see this, it seems a little weird, right? 40 divided by 60 instead of 40 out of 100. You guys ever go to the track, play horses? Never? Never? No, never. How about you guys online? You ever go to the track? Somebody must have gone to the track at some point. That's kind of an old, you know, in the 50s and 60s, that, you know, it was a real guy thing to go to the track and hang around by the rail and, you know, bet the horses. And they even had they had off-track betting in New York, where instead of going to an illegal book, there used to be illegal bookies all over the city. And of course, it was run by the mafia and stuff like that. So these have, you know, your local barbershop would be like a drop off of bets and stuff like that. In my neighborhood, there was this shows you how long ago this was. There was a bowling supply store that was the local bookie, and he would take horse racing bets. But then in the 70s or late 70s, the city instituted off-track betting, where you could go to a storefront that the city ran, and you could bet on horses that were running that day at one of the tracks. You can even watch that TVs. You can even watch them running. And the way betting works is that the track never loses. The way it works is that everybody bets. There's 9 horses running, let's say, and you bet on horse 1, somebody else bets on horse 2, somebody else bet 3, 4, 5, and so on and so forth. And all of that money goes into a pot. The track takes 15% of that out, and the rest of the money goes to the winner of the race. People have picked the winners in the race, right? So you're basically betting against other bettors, not the track, not like the house, like in a casino, right? So the way to make it convenient to pay off bets, if the odds would be displayed, not the risk, not the rates, but the odds would be displayed on a big board. So you would know that at this point in time, when given that this much money had been bet, and the track took their 15% out, that if you bet $10, that you would get so much money for your bet, right? Usually based on a standard $2 bet. So, for instance, if the odds were 3 to 1, right? What that says is, if you bet $4, if you bet, for every dollar you bet, you would get $3 back. And what the odds represent is that if that race were run 4 times, that horse would be likely to win 1 out of the 4 times, 1/3 of the time. So the payoff is 3 times, that 3 to 1. That's really what you look at. And that's really kind of what the odds are here. In other words, you're looking at, like the number of people who have diabetes versus the number of people who don't have diabetes. In other words, if that race were run that many times, how many times the horse would win, how many times the horse would lose, right? So it works the same way. Why they use odds ratio instead of relative risk ratio on many studies, we can discuss that another time. But it's not, I can tell from your face, it's not as intuitive a way of describing the increased risk as relative risk is. But we use both, right? And it's, as it happens, odds ratio tends to show up in more studies than relative risk. But the real key here is, when we were working with chi-square, what determined whether we could reject the null hypothesis? It was the whether or not the chi-square statistic exceeded the critical value from our table for that number of degrees of freedom. And what determined it for relative risk and for odds ratio? Well, for relative risk and odds ratio, what determined it is whether or not the value 1 was within the confidence interval for your odds ratio or relative risk. If it was, it means that you weren't sure that it was different than 1. If 1 is outside of your confidence interval, you can have at least that level of certainty, 95%, that the true relative risk is not 1. In other words, not the same for, in this case, males and females. So this is a lot to digest in one sitting, isn't it? Right? We did odds ratio, relative risk, chi-square, critical values, confidence intervals, and so on and so forth. That's a ton of stuff to digest here. Okay, so what I'm going to do now is I'm going to give you well, first, before we do anything else, how would we really apply this? Let me just get to this and erase this. How would we, in real life, how would we apply this? Well, chi-square, you could use Excel to calculate that. It was a pretty simple calculation, except for the fact you would have to go to the table for the critical value. Actually, I think you could look up the critical value in chi-square too if you needed to. Okay, so, but we could also do this using SPSS. So I am going to open up SPSS. Okay, say open. Data. I'm going to navigate to my desktop. And these files are on this week's folder for the weekly materials on Blackboard. So I'm going to open up this one, smokers and smokers income age. I think that is a file that will help us out. But let me get it open. And oh, look at this. Okay, good. So smokers age, that looks like the age of the smoker. Let's see the variable view. Yeah, it says smokers, but it says, oh, hang on a second. What is that? Oh, smokers per 100 population. That's the rate of smoking in different populations. In other words, we have age ranges. Okay, let's click in there and see what the age ranges are. Age range 1, 2, and 3. They're not really defined. Let me go in there and define them. I'm going to say 20 to 30. Oops, I should have said add. Try that again. 20 to 40. I'm going to say 20 to 40. Change. This one I'll call 40 to 60. Change. And just for the hell of it, I'll call this one 60 to 80. Make a little bit more sense that rather than just saying age range 1, age range 2. Income levels. Okay, income level 1. Okay, I'm gonna change that a little bit too. I'm gonna put 2 income levels. Okay, and well, smokers, I can't define that because that's a number, right? That's the percentage of smokers. Smokers per 100 population is a percentage of smokers. That's a scalar variable. Okay, now let's say that my income levels were, instead of that, I'm going to say change income level, let's say income level below the poverty line, and 2 is above the poverty line. I'm simplifying this a little bit because I think it'll make it easier to understand. Okay, so let's take a look at what we have here. So first of all, number one, we know now that chi-square, odds ratio, relative risk, you only use them with categorical variables. You don't use them with numerical variables like percentage of smokers or smokers per 100 or something like that. That's a number, right? If you go back to the data, you can see that that's a number. These are categories. In fact, if I go up here to view and turn on the value labels, you can actually see what each one represents. This is above the poverty level. Oh my goodness. I'm going to have to change this because not all of them. I eliminated some categories here. I just left the 1s and the 2s. Okay, so go back and look at this view, value labels. Okay, do you guys want to close the door? We're having a domestic dispute outside in the hallway there or something. Okay, that's not the worst. The worst is babies crying in the back. That's why I make sure everybody's silenced, The most distracting is there's something about a baby crying that gets an adult's attention like nothing else. I went on a trip. I don't want to make you think I gamble all the time. I do not. I very rarely gamble, especially since I know statistics. But it just happens that the company I used to work for during the day, once a year would take their best customers on a trip to Atlantic City. And they would get one of these luxury buses, had like tables and booths and TVs and stuff like that. It was beautiful. And they would get about, like 20 customers, and they'd bring us along to entertain the customers, the engineers and the other people and entertain the customers. So there'd be about 20 customers, maybe about 10 of us, right? And so some wives would be there, and some of the other among the engineers, some women and stuff. So the TV would have a little, back in those days, that a VHS tape plug in, right? So not everybody's taste in movies was the same, right? So this one trip we took, on the way down, we watched, they were playing Terminator or something, like either Terminator or some Arnold Schwarzenegger movie. I don't even remember what it was, but there were bombs going off, blasts, explosions, machine guns, and we were sitting there, talking, playing poker. Nobody was, and this was on in the background. Didn't disturb anybody. On the way back, they put in Three Men and a Baby. Remember that movie, Three Men and a Baby? Every time that baby started to cry, you couldn't have a conversation. I mean, it's primal. You hear a baby crying, you can't think. It's like that bomb's no problem. Baby crying, nobody could concentrate. We couldn't play poker. Couldn't look at the cards. So at any rate, so yeah, there's certain sounds that are really distracting, and what's going on in the hall is really distracting. But at any rate, so you can see these value labels that you can see that what these represent. Right, some of these people below the poverty level, above the poverty level, the different age ranges, and so on and so forth. Okay, so let's say that we are interested in knowing, this wasn't a great example here. Let's say I want to know which of these are my risk factors. Is it more likely that you are going to be below the poverty level if you are young, middle-aged, or older? Okay, so my exposure is going to be age, which I have 3 categories for age, and my outcome is going to be income level, below poverty level or not below poverty level. So I am going to say, well, how am I going to organize this data? Well, in order, when I'm working with categorical variables, I organize it by using contingency tables, the tables I just drew. So I'm going to go up here to analyze. I'm going to go to let's see what I have here. Let's see, descriptive statistics. Oh, look at this. There's a category here under descriptive statistics called crosstabs. So I'm going to click on that. And it comes up where I can tell it what variables to put in the rows and what to put in the columns. So in our case, the exposure, right, is the age range. Are you older people or younger people more likely to be low income? My outcome is the income level. So I'm going to put that in columns. So this has 2 values. This has 3 values. So our table should be 3 rows and 2 columns. And here's our table right here. So our table is, let's see, we had 2 out of 5 people that were below poverty level. In the young and middle age, we had 3 out of 5, and the older ones we had 1 out of 5, and so on, right? So if I want now the point is, well, how likely these numbers are really tiny? So it's going to be this is not really a great example. Now, if I wanted to know, well, what's the likelihood that these differences are due to real differences in poverty levels for the entire population of people in these age ranges, or if the differences are only due to chance? Well, let's take a look at what our expected values would be. So I'm going to go to Analyze, Descriptive Statistics, and Crosstabs. And now I'm going to go in here, and in cells, if I click in cells, I can ask it to give me the expected values also. How does it calculate the expected values? it calculates an overall rate for poverty level, and then applies it to each population. In other words, overall, let's say the rate of poverty, the poverty level rate is 30%, then you would expect 30% out of 5 people to be, actually it's 2 out of 5, so it's probably 40%. So you would expect, so these are the expected values. I would have expected to get 2 out of 5, so I got exactly what I would have expected in this case. For the next age range, I got fewer than I would have expected. My expected table, notice how it combines the 2 tables into 1 table, but you could actually draw this as a second table, where these expected counts are the other table, right? So how would we calculate chi-square in this situation? We take the expected values minus the observed values, square them, divided by the expected values. There's an issue with the sample size here. We can't really do this properly because of the sample size. So now, what if I want to actually go ahead and calculate this, chi-square for this? We could either do this in Excel or with calculators, do our observer and do it for each one of these cells, right? And there are, let's see, it's 3 rows, 2 columns, there's 6 cells. Do comparison, square them, divide by the expected values, calculate what each value was, add them all together, and then compare it to the critical value. Okay, and the critical value we would look up. So it's 3 minus 1 is 2. 2 minus 1 is 1. So the degrees of freedom are 2. So the value that we would need, the critical value of chi-square would be 2 degrees of freedom would be 5.99. Okay, it's not going. This is, like I said, not going to be valid because the sample size is so small. But now I could go up here to analyze. I could go to descriptive statistics. I could go down to crosstabs, and now I can go up to statistics and ask it to calculate the chi-square value for me. I'll click continue and say okay, and it will calculate the chi-square value for me. And the chi-square value is 1.667. What did I say the critical value was again? It was like 5, right? Something like 5. So in this case, the value of chi-square I calculated is only 1.667. The critical value was 5. So I haven't exceeded the critical value. So I failed to reject the null hypothesis. No surprise given how small this sample size is, right? Well, the other thing I get here, notice it calculated degrees of freedom, it's just as we did. And then it gives me a significance or a p-value, a probability that we would get this big a number if the null hypothesis were true. Okay, so we would get this extreme of chi-square value 43% of the time if the null hypothesis were true. We need that to be less than 5% in order to reject the null hypothesis. So the fact that this is less than the critical value for chi-square from the table, and that this is bigger than 0.05 tells us we fail to reject the null hypothesis. Well, now, what if I want to do odds ratio and relative risk? Will SPSS do that for me? Well, sure it will, but there's a little bit of a problem here. I'll show you the problem. Oops, got the wrong one there. Analyze, descriptive statistics, crosstabs. And I'm going to go into statistics again. And to calculate the risk, relative risk and the odds ratio, we click that. Click continue and say okay. And we get our table again. We get chi-square calculated again. Oh, what happened? We got an error. That's the odds ratio for age range. Blah, 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 blah. Risk estimate statistics cannot be computed today. Only computed for a 2x2 table. So we can only do this for a 2x2 table. There are ways for us to get around this later on that we can talk about if you want to break down your data into 2x2 tables instead of the large data. But you can use chi-square for any number of rows and columns that you want. Okay, so I am going, let me see if I have a better example here. Okay, so you can see that we have a mechanism for doing this in SPSS that saves us quite a bit of work. Let me get back to my let's see, data files. paper. Let's open this one. One of the files that we have is stenosis and smoking. Oh, I didn't need to do that. Yeah, close tabs, yep. Okay, let me get SPSS. Open data. This again is on Blackboard. Desktop. That's what happened. I went into the Innova folder instead of the one I wanted to go into, which was chi-square. Went into the wrong folder for the data files. Naturally, I wound up with one that was better for analysis of variance. Okay, let's try stenosis versus smoking. Okay, so what does this data set tell us? We have three variables here: smoking, disease, and gender. I'm going to go to my variable view so I can see what these represent. So smoke, that variable smoke is a categorical nominal variable. These are all nominal variables. Smoke, let's see what that represents. Label, let's go in here. One represents the person's a smoker. Two says that he's not a smoker. Okay. How about disease? Presence of aortic stenosis, right? Hardening of the arteries. Okay. One is the disease is present. Two, the disease is not present. And the third one is gender. And in that case, 0 and 1, I'm going to leave it the way it is. Just keep in mind it says 0 and 1 instead of 1 and 2. Okay, so there's a few things I can look at here. For instance, these are all nominal variables. There are all of them have two possible outcomes: yes or no, or so on and so forth, gender, male and female, right? So anyway we look at it, we're going to get 2 by 2 tables. So the outcome, what's the disease? The disease is probably aortic stenosis. That's the outcome. So that's probably going to wind up in my columns because it's the outcome or disease. What's going to wind up in my rows? Well, I could look at whether or not smoking makes you more likely to have an aortic stenosis, right? To be a row which is non-smokers and smokers and non-smokers. We could also look to see if gender affects your likelihood of having aortic stenosis. In other words, whether there's an increased risk if you're male or female for aortic stenosis. So what I'm going to do is I'm going to start with gender. I'm going to go up here to analyze. I'm going to go to descriptive statistics. I'm going to go to crosstabs. And I'm going to move into my columns. I am going to move the presence of aortic stenosis. In other words, whether or not you have the disease. And into the rows, I'm going to move gender. Okay, so now I am going to go step by step. You don't have to go step by step. You could do it all at once. I'm going to go into statistics, and I'm going to say, okay, give me the observed values, just the observed values. And I'm going to go make sure in statistics there's nothing checked off. Okay, good. So I just want to see the table, the crosstabs table for this. I'm going to click OK, and here we go. Here's the crosstabs table. Okay, so what do we have? We have gender versus the presence of aortic stenosis. So we have 109 females and 106 males, and it looks like 36 out of 109 females have aortic stenosis, and 62 out of 106 males have aortic stenosis. So, you know, it looks like the actual rate at which people get aortic stenosis in this population is 98 out of 215. If I combine these, there's really 215 people, 98 of which have stenosis if I ignore what their gender is. So it looks like in this population that the rate of aortic stenosis is almost 50%. So in this case, let's see, 36 out of 100 or so, the women only seem to be at the rate of 36%, and the men seem to be at the rate of around 60%. Seems to be a difference in these two tables, right? Let's take a look at what the expected values would be. How would you calculate the expected values? The way you would calculate the expected values is you would combine all of the people who don't have aortic stenosis, all that do have aortic stenosis. So you have a total for people who have the disease out of the total number of people. 98 over 215 is the prevalence of aortic stenosis. So if there's no difference between male and female, you would expect them to both have the same rate of aortic stenosis. So now that you know what the prevalence is, for argument's sake, say it's 50%. Now that you know what it is, if you go to the total here, 109, you would expect half of those people to have aortic stenosis. So you would your expected value would be 54 people and roughly 54 people in the yes and no for females. How about males? 106, I would expect 53 and 53. So your observed values would be 54 and 54, 36 and so on and so forth. Just happens to be 50% for this case, not always 50%, right? But you can see that there's a difference between your observed values and your expected values. I'm actually going to go over here, analyze, descriptive statistics, crosstabs, go into cells, and I'm going to say, calculate my expected values. And say, okay. And you can see that there's a difference for males and for the expected values in each one versus the observed values. The observed values here are called a count, observed values. And also notice something else. The expected values, because they're calculated, they're not real world, they are 49.7, 59.5, they're fractional, right? You'll never get, in observed values, you'll never get a fractional value. Because the person's either going to be in one box or the other. It's not going to be a fractional person in real life, right? So they're always going to be whole numbers, right? So this is what my expected values and my observed values look like. I'm going to go back in here to analyze, descriptive statistics, crosstabs. I'm going to turn off the expected values. They're just noise anyway. I don't want to see them right now. But I will turn on the percentages by rows. And then I'm going to say OK again. So now let's see what I got. Well, now it tells me, gee, it actually calculated the percentage of women, females, who have aortic stenosis, right? That's 33%, which is 36 over 109. That's the same as the risk, right? And for males, 62 out of 106, that's 58.5%. So what would be my relative risk for females versus males? Well, 33% divided by, right, because that's A over A plus B, right, 36 over 109, right? That would be 33% divided by 58.5%. So my relative risk is, let me do it on my calculator. Clear? 0.33 divided by 0.585 is equal to 0.56. What does that tell you about the relationship for aortic stenosis, the risk of aortic stenosis in males and females? 0.586. What does that tell you about that? That number is, what is that number? Is it bigger than 1 or less than 1? It's less than 1, right? 0.58, right? That ratio is less than 1. What does that tell you? That tells you that being female is protective. It reduces your risk, right? SPSS always works with the number on, with the arranging these things alphabetically. So it's saying that since it's less than 1, the difference is protective for females. Now, again, as far as the risk ratio is concerned, what are we really concerned about? We're really concerned that the risk ratio, the confidence interval, does not contain the number 1, right? Okay, so let's go ahead and actually do a calculation here. Let's go up to Analyze, Descriptive Statistics, Crosstabs. Okay, except this time I'm going to go into Statistics. And I'm going to say, calculate the chi-square value for me, and calculate the risk for me. Now, we already know the relative risk is going to be 0.33 divided by 0.85. But did I say what that was? Did I calculate that? Yeah, 0.56. Okay. So I already know what the relative risk is, but I didn't calculate the odds ratio because the odds ratio would be slightly different number based on the cells. Okay. So I'm going to calculate chi-square and I'm going to calculate the risk. I'm going to click continue and click OK. So SPSS does these calculations for me. Here it recreates a table again. Okay, so now my value of, first of all, number one, this is a 2x2 table, correct? Right, 2 by 2, right? My value of chi-square that I calculate is 14.047. Can I reject my null hypothesis that there's no association between gender and risk of aortic stenosis? What do you guys think? Can I reject my null hypothesis? You guys remember what the critical value of chi-square was for a 2x2 table? Right, that's 2 rows minus 1, 2 columns minus 1, 1 times 1 is 1 degree of freedom. Remember what it was? It was 3.4, I think 3.41 or 3.48. So if my critical value is 3.48 for a 2x2 table, can I reject my null hypothesis? Right? The answer is yes. Right? You guys agree with me? Okay. What else tells me I can reject my null hypothesis? What is the probability that I would get this big a value if the null hypothesis were true? It's less than 1/10 of 1%. So if that's less than 5%, that's also evidence I can reject my null hypothesis. Okay, so next, what else did it give me here? Oh, look, it gave me risk estimates. Okay, so this first one is the odds ratio. And the odds ratio, if you calculate it, you could do this, you could actually go up here and do that if you wanted. It would be 36 divided by 73 over 62 divided by 44, and it would come out to 0.35. Well, what's my null hypothesis for the odds ratio? Null hypothesis is the odds ratio is equal to null, is equal to 1, and my alternative hypothesis is it's not equal to 1. Well, in fact, we calculated it, given this data, this sample data, to be 0.35, but then our confidence interval for the true population proportion of a population odds ratio is 0.201 to 0.610. Is 1 between those two numbers? It's not. So that means we're 95% sure that it's not 1. Since it's not, so 95% sure it's not 1, we can reject the null hypothesis that the odds ratio is equal to 1, right? That there's no difference in the odds of having aortic stenosis if you're male versus female. Well, how about the relative risk? Remember we calculated that I calculated that down here. It went away. It was the same thing here. It was 0.565, right? And again, for the relative risk, what's our null hypothesis? That the relative risk is equal to 1, that there's no difference in risk for the two groups. Our alternative is that it's not equal to 1. In order to prove that it's not equal to 1, we have to make sure that the confidence interval, 95% confidence interval for the true population relative risk is not 1. So if the confidence interval does not include 1, we can reject the null hypothesis. So we have 3 ways of proving the same thing here. 4 ways. One way is we exceeded the critical value for chi-square. Second way is our significance, our p-value is less than 0.05 for chi-square. Third way is our odds ratio excludes the value 1, null hypothesis with odds ratio is equal to 1, and our relative risk excludes the value 1. A relative risk is equal to 1, which was a null hypothesis. So all 4 of those point to reject the null hypothesis. And they should all agree, anytime that you do it. Okay, so what I'm going to do now is that I am going to have you guys give this a try. The same data sets, stenosis and smoking, if you go to Blackboard, our page on Blackboard, and go to weekly materials, and go to the data files for this week. And go to data files. You can right click on stenosis and smoking, right click and download it, save it to your desktop over here, and then open it up in SPSS. Either double click on the file on your desktop or start SPSS and navigate to the desktop, whichever is easier for you. So download that file and repeat this analysis, except this time do it for smoking instead of gender. Do exactly the same thing I did. You don't have to do 9,000 things though. You can just do, check off all the things you want at one time. You don't have to do, observe values and then go back and separately do expected values, and then separately do percentages by rows, and then separately do chi-square, and then separately do risk ratio. Right? You can do it all at once if you want to. But you guys, I'll give you guys about 10 minutes. So give it a try. See what you do. I'm not going to look over your shoulder. I want you to actually work on it. Give it a try, and then I will go over it so you can see if you managed it okay. Okay. So I'm not putting you under any tremendous pressure here. It's not a test, but I want you to actually physically give it a try while I'm still here to answer any questions if you have them. You guys online too, give it a try. I'm going to pause recording. Remind me to put recording back on rather than have 10.
This conference will now be recorded.
Okay, so we're back. Hopefully you got a chance to at least give this a try using SPSS. I'm going to go through the process that I would use. And this time I'm not going to bother to kind of do that stepwise thing where I created the tables and the percentages by rows and so on and so forth, but I'll just go straight to the actual analysis. So for starters, what would my null hypothesis be if I wanted to examine, given this data, whether or not there's an association between being a smoker and developing aortic stenosis, what we call disease here? Okay, so what would my null hypothesis be? First, I want to set up a null and an alternative hypothesis. So my null hypothesis, all right, on here, my H0, my null hypothesis is that there is no association between the smoking status and whether or not a person developed aortic stenosis. My alternative hypothesis is that there is an association, that whether or not you're a smoker does affect whether or not how likely you are to develop aortic stenosis, that there is an association between smoking and aortic stenosis. So now that I've established my null and alternative hypothesis, I have to determine, well, how certain do I want to be that I can reject my null hypothesis without being wrong about that, not making a type 1 error. So you could say, conventionally we would say alpha is equal to 0.05, 5%. In other words, our result would be that we want to get an outcome that is has less than 5% chance of being of the null hypothesis being true. In other words, we'd only get that big a chi-square value less than 5% of the time if the null hypothesis was true. In other words, in a sense, saying that there's less than 5% chance we would be wrong if we reject the null hypothesis. We would make a type 1 error, reject the null hypothesis. Real statisticians wouldn't phrase it that way. They'd phrase it the former way, that the likelihood of the outcome would be less than 5%. But it's kind of like saying the same thing. But if you're talking to a statistician, use the first way instead of the second way. So alpha is equal to 0.05. If I really wanted to be sure and I wanted to be more rigorous, I could say alpha is equal to 1%. So we can be 99% certain that we can reject the null hypothesis. Okay, so in that case, our critical value for chi-square, the number that chi-square has to be, becomes a larger number. So if you look at the table, and I'll bring that up for a moment. If you look at the table for chi-square, you'll see that for 1 degree of freedom, a 2 by 2 table, for 1 degree of freedom, then chi-square for 5%, alpha is equal to 5%, is 3.841. If I want chi-square to be 1%, 99% certainty, you would have to exceed 6.635 instead of 3.841. That's a different critical value. Okay, so keep that in mind when you set that in the beginning. Okay, the other thing I'm going to do is I'm going to actually I'm going to calculate my relative risk for smokers versus non-smokers, and my null hypothesis is going to be relative risk is equal to 1. In other words, is the ratio, risk ratio, relative risk, no difference between the risk for smokers and non-smokers. Therefore, since the risk, the denominator and the numerator are the same, that's equal to 1. Okay, and my alternative hypothesis is the relative risk is not equal to 1. So when I actually calculate the relative risk, the important thing there is that whatever the relative risk comes out to be, let's say it's 2.1. The important thing there is that the confidence interval, my 95% confidence interval for the relative risk, not just the 2.1 I calculate, but my confidence interval does not contain 1. Okay, does not include 1. Sorry for the scratches there. Does not include 1. Similarly, odds ratio, my odds ratio is equal to 1 is my null hypothesis, and my odds ratio is not equal to 1 is my alternative hypothesis. And again, in order to reject the null hypothesis, my confidence interval for my odds ratio should not include the value 1. Right? No, not 1. Okay, so let's go ahead and actually calculate it now. Okay, so I'm going to go up here to Analyze, Descriptive Statistics, Crosstabs. Okay, now again, I'm going to put these back over here. Whoops. Back over here so I can decide what I need. In the columns is going to be my outcome, my disease. So obviously that's going to be aortic stenosis. In my rows is going to be my exposure. Well, we worked with gender before, and now we're looking to see if smoking is an important exposure in terms of risk for aortic stenosis. So in our rows is going to be smoking status. Top row is going to be smokers, bottom row is non-smokers. That was 1 and 2. Okay, and presence of aortic stenosis. The left column is people with aortic stenosis. The right column was people without aortic stenosis. These, remember, we're working with a sample here, not the population. So our real interest is in our null hypothesis, alternative hypothesis, which have to do with the population. Okay, so that's going to be our presence of aortic stenosis. Again, 1 have it, 2 they don't have it in those 2 columns. So now I'm going to go to statistics. I'm going to ask SPSS to calculate the chi-square value and calculate the risk. Okay, risk includes risk ratio or relative risk, and it includes the odds ratio. So I'm going to say continue. I'm going to click OK, and magically the output table will come up. And let's see what we wind up with. Okay, without having to calculate it ourselves. Remember, what we would have had to do is say our observed values minus our expected values, 54 minus 57.4 squared divided by our expected values, and so on and so forth. I would have had to do calculations for each one of these cells, add them all together, take the sum of them, add them all together, and wind up with the value 9.48, which SPSS has done for us. So I know 1 degree of freedom, remember degrees of freedom, is the number of rows minus 1 times the number of columns minus 1. 1 row, 2 rows minus 1 is 1. 2 columns minus 1 is 1. 1 times 1 is 1. So 1 degree of freedom, we know the critical value is 3.84, I think, 3.48, something like that. And the actual value of chi-square we calculated for this table, for these differences, is 9.48. So we can reject the null hypothesis because we've exceeded our critical value for chi-square for the degrees of freedom and the alpha error that we're willing to accept. Okay, and similarly, SPSS actually calculates the actual probability that we would get this outcome if the null hypothesis was true, and it's less than 1%, it's 0.2%. Since that significance or p-value is less than 5%, goes along with the chi-square value, we can reject the null hypothesis. Here's a quick question. If let me just look this up again. Oh, that's not the one I want. See if I got it still here. I closed it. Let me get it. Yep, I had it just there. Oops. Okay, so 1 degree of freedom was 3.841. Okay, so if the chi-square value was 3.841 that I calculated from this table, what do you think the significance would be? What number would we see in that box? If it's exactly what we need to reject the null hypothesis, what probability would we see in that box? It would be exactly 5%, right? Because they go together. If the chi-square value is bigger than the critical value, then the significance is lower. It becomes less than 5%. The bigger the chi-square value becomes, the smaller the significance or the p-value becomes, right? So that's the critical value and that 5% for our significance, they go together, right? So that's why you want the chi-square to be bigger so that your p-value can be smaller than 5%. Okay, and the next one I'm going to find, don't worry about continuity correction. I'll talk about that in the future. The next thing we're going to go do is go look at our risk estimates. And our top column here is for odds ratio. The odds of having aortic stenosis, if you are a smoker versus a non-smoker, the odds to 2.36 times is great for a smoker versus a non-smoker, right? So it looks like we're going to reject our null hypothesis because that's different than 1, right? Which would be the odds are the same. But can we? Well, we have to check our confidence interval to make sure that we're 95% certain that it's really different than 1, not just that our sample was different than 1, but the true population odds ratio is different than 1. And in fact, the confidence interval is 1.36 to 4.1. So 1 is not in between those two. So we're 95% sure it's different than 1, okay, for our population. And the next row is our odds ratio. And our odds ratio was determined by 54 out of 94 divided by 44 out of 121. And that, divided by 124 out of 21. And that was a simple way of calculating odds ratio. 1 point. And again, our odds ratio, same thing. The null hypothesis, a relative risk rather, relative risk or risk ratio is equal to 1. Null hypothesis, not equal to 1 is our alternative hypothesis. And 1.580, that's great. It looks like it's 50% greater risk from that perspective, from perspective of risk. But we have to make sure that the true population is different, not just our sample result. And when we calculate our confidence interval, it tells us that the 95% confidence interval for the true population risk ratio is 1.18 to 2.12. Right? Well, what does that tell us? It tells us that it's different than 1. We're 95% sure is for the populations between these two numbers, which means we're 95% sure it's different than 1. So we can reject the null hypothesis there. 4 ways that we rejected the null hypothesis. Okay, so that's what we did. That's it. That's chi-square. That's odds ratio. That's how we deal with categorical data. So now we know, how to calculate confidence intervals for means, population means and proportions. We know how to do compare the means of 2 groups using the t-test. We know how to calculate the means of more than 2 groups doing the analysis of variance. And now we know how to determine whether there's a difference whether there's an association between categorical variables using chi-square or odds ratio or relative risk. Okay, and they're not ridiculously complicated calculations, and they're not hard to do, especially if we have SPSS tools like SPS to do with them. Okay, so next week we're going to review all this stuff, and then the following week we're going to have an exam. It'll be an online exam similar to the last one, and we'll figure, I'll fill you in next week on what we'll do. And hopefully, like after next week, I will also maybe do some sort of online Q&A or something like that at some other time, maybe in the evening or on the weekend or something like that. If you want to, if you want to review some stuff. Okay, so I think it's a good time to call it a day. You guys want to stick around for another 2 hours, or you had enough, or no? I guess not. Okay. So you guys online, thank you for listening in, and I'll try and post this. I got to convert this, and I'll try and post this as soon as possible. So take care. Good night.